Welcome to qnawire.
We need to prove that the angular momentum of some arbitrary system at the point B is equal to the angular momentum at its point A plus the position vector from point A to B cross its linear momentum. And we also need to prove that whenever points G, A, and B lie on the same fixed axis, then the angular momentum at point B has to be equal to the angular momentum at point A. So I drew out a simple diagram here that we will reference whenever we're writing the different equations, whenever we're trying to prove these two different expressions. So we'll start by proving this first equation here. So what we can say is that the angular momentum about some point A is going to be equal to the angular momentum about the point G plus the position vector from point G to A cross its linear momentum. And we can say the same thing for the B position. So the angular momentum at the point B is equal to h of G plus the position vector from point G to B cross its linear momentum. So what we're going to do now is we're going to take h of B and subtract h of A from it. So we're going to have h of B minus h of A, and we can write that as R of GB cross MV minus R of GA cross MV. And we're going to take this h of A and add it to the other side. So rewriting this, we have h of B is equal to h of A plus R of GB minus R of GA cross MV. And we're going to take these two position vectors and separate them out into their different components. So we have h of B is equal to h of A plus these components, these vectors separated. So we're going to have R of G, the point R of G, minus R of B plus R of A minus R of G, and then cross the linear momentum. And then we notice that these two terms will cancel, and we'll be left with this negative R of B plus R of A. So we can finally write this as h of B is equal to h of A plus the position vector from A to B cross its linear momentum. So now we'll prove the second equation. And before we start that, I'm going to go back to our diagram. And I'm going to redraw it a bit. So I'm going to move this B point. And I'm going to move it here. So now point G, point A, and point B will lie on the same fixed axis. And also notice that it is rotating in the counterclockwise direction. So that means that there's going to be an angular velocity pointing upwards in the same fixed axis as G, A, and B. So now to prove this equation here, so in order for this to be true, this part of the equation, or R of AB cross MB, has to be equal to 0. So we can say that R of AB cross MB is equal to 0. And then next what we can write that big W, where big W is an angular velocity vector. So I'll label that with a vector sign. That's going to be equal to the magnitude of that angular velocity times the unit vector across the fixed axis where G, A, and B lie. And we know that we can write that this V vector is going to be equal to the W vector cross the R vector from A to B. And since we know that this expression here is true, we can next write that R of AB cross M of this W vector cross R of GA is equal to 0. And I'm actually going to write, so this W vector, I'll rewrite it as just this omega and the unit vector. So now we can say that this unit vector cross this unit vector cross R of GA is equal to 0, since we know that the points A and B are parallel on the fixed axis. So now I'll write some vector u. So we have a vector u that's equal to the unit vector cross the R vector from point G to A. And this unit vector cross that u vector is going to be equal to 0. So if this is 0, that means that this u vector is either equal to 0 or is parallel with the unit vector that's on the fixed axis that's also on the points G, A, and B. So now I'll write that u is equal to the unit vector cross the position vector from G to A, which is equal to 0. So this proves that G, that point G, is on the fixed axis.